Hey everyone, and welcome to Lesson 7, Endianness and the Building Blocks of Computer Networking. Now if you'll recall in the last lesson, I said we were going to talk about this issue of endianness. So what I've done is I've kind of drawn this diagram here to illustrate the difference between big-endian and little-endian. Now this needs some kind of historical context, and from what I've researched, it seems that there was a novel written in the 18th century by Jonathan Swift, and this novel essentially there were two races of people called Lilliput and Blefuscu, and one of them decided they wanted to, and they had a big conflict in this novel, and one of them, called the big-endians, they wanted to break eggs on the bigger half of the egg, and the others the wanted to break, and that was the traditional way of doing things, and the others wanted to do it on the little end, break the egg on the little side. Now this conflict in this novel was actually incorporated much later on, generations later, and currently affects computer systems today. Now, traditionally, things have been done with the PowerPC architecture. Things were done in the classic way with telephone systems, with the internet. Everything used to be big-endian, but then Microsoft came along and they decided they wanted to do things in the little-endian way. So all the different architectures, that's x86, x64, 32-bit and 64-bit operating systems, as well as their PowerPC architecture, are all done with little-endian. So both of them are still very much in use, but it's certainly it's certainly still something which is going to be very important to understand as we move into MIPS and also as we move into networking, because these things affect kind of the interpretation and the compilation of things very much. So what I want to do first is draw your attention here. I can see I put a little E here, and I should have really done a capital E, but otherwise the graph, the image is fairly sound. So if we look at big-endian, this is the traditional way of doing things. We can see that as we go right, the bits become less significant. These are supposed to just represent bytes. So this byte here, we've got 0 and the 1, 2, 3. So so the bytes get less significant as we go to the right. And conversely, in the little-endian system, the bytes get more significant as we go to the right. So let's just look at 1027 as a 4-byte integer in both the systems. Now we write it down like this. We can see we have this byte here, the second byte, the third byte, and the fourth byte, and that should be fairly clear to you that the 1027 is this number here, because obviously you've got a 1 in the 1 column, a 1 in the 2 column, that's 3, and then if we go 4, 8, 16, 32, 64, 128, 256, 512, 1024, so 1024 and 3 is 1027. So we look at how it's represented in both systems. We can see they're basically the converse of each other. So in the big-endian system, the addresses at 0 and 1 are all zeros, and 2 and 3 have the details. You'll notice that's actually the same as the image above. This is the same as the image above. However, in the little-endian system, which may end up being, it's probably seen as more important now because it's the newer system. It's breaking away from the traditional way of thinking, and it's the way that progress is made. The MIPS system we'll be using actually uses both, which is interesting. So we can see that conversely it affects things in a different way. Now, so yeah, that's endianness. It's a really important concept to understand, because it's not immediately apparent. But when you're doing like assembly code and you're really trying to write, some of these low-level systems, you really need to understand the fundamental difference between these two. And like I say, it's good to know the historical context as well. So like I say, this lesson is also about the building blocks of computer networking, and they go hand in hand. Endianness is something which is is paramount when you're doing the networking, looking at networking functionality, and networking, it really is required for a whole range of functionality. So if we look at what we've got here, we can see that it's required for video conferencing, it's required for database remote access, file server providing access to file system. So I could have put many more there. I could have put the World Wide Web in there. I could have put mail servers like Exchange or Thunderbird, but I've decided just to put a few down there because to avoid overloading this section. So now, for information request and exchange, there must be a standard set of commands and data formats, and this is protocol. So for anything to actually happen, we need to have standardized commands and formats, data formats, so we actually know how to shift things up and shift things down, and and how to communicate. And this is of key importance, because otherwise everything would be a kind of tangled mess. But if once we micromanage the data in such a way, and it's also related probably to microeconomics, then we can understand how to move the data, and how to provide a conducive system that works for both the human brain and the binary computer brain in inverted commas. So now each layer uses the service provided by the layer below, does its job, and then provides a service to the layer above. And each layer may have several different protocols. Now what I want to do is give you kind of a bare bones guide to each of the layers, and also the functionality of the layers. Now the interaction between the layers is important, but to actually understand fundamentally the sort of mathematical sort of foundations that I mean, it's not really mathematics, it is just invented, but there is still kind of function definitions, and sort of specifications that we can kind of we have to illustrate before we move on to the the interrelationship and the kind of socialization between each of these layers. Okay, so there's a layer at the top, human. So that should be fairly that's pretty obvious. So we've got the human, and then let's go from the human now, and let's go down to the computer. So first of all, we have the applications. So the applications, we can understand that. We go in applications. I'm in Notepad now, for instance. There's an application. And then we have the transport layers, the transport layer, and this is the one that transports internally within the direct network. And then we have the network layer, and then we have data link layer, and then finally the physical medium. So one thing you notice is that I've also put some little comments on the right hand side there, and the reason I didn't actually read them out is because the way we want to go is we want to go up. So if we start with physical medium, then the physical medium, through encoding the wires and all the switches and things, will transfer bytes to any directly connected machine. That's what the data link layer does. And then we go up, and then we can go to the next level, can't we? We can say that it transfers bytes to any machine. So it's not just the directly connected machine; it's any machine now. Now we're at the IP level, and then we go to transport layer, and that transport bytes between programs, and then finally we go to the application, and then we're back at the human. We use the transferred bytes. Okay. Now this is not making that much sense at the moment. I'm going to try and illustrate this a little bit further now, because these are the key layers. These are the key names you need to remember. So you've got the application layer, transport layer, network layer, data link layer, and the physical medium. Now, luckily, the human and the physical medium, we're not going to go into too much detail. They're subjects for either, I suppose, psychology or semiconductor physics, depending on which one you want to choose. But we are going to be looking at these layers in between, because these are the layers that transcend, that create those bridges. And in between each layer we have the protocols acting. So these protocols are acting between the layers. Okay, so they're providing services, and they're using functionality. So let's look at the data link layer. Now, if we remember, the data link layer is right next to the physical medium. So this is on your own network. This is on your own system of computers. Now, the data link layer, it transfers packets of bytes. It would be 1500 maximum bytes on the Ethernet wired to the same Ethernet switch. So when we're dealing with data link, we're only dealing with the internal network. It's just the internal network. There's nothing else. So for instance, we could there's various standards, aren't there? We could be using 802.11 the wireless local area network, 802.3, and that's the Ethernet. That's you may have heard of 802.11. Just because it's announced when you get all the routers, but 802.3 you may not have heard of, but that's because it's so standardized that no one even mentions the sort of code. And how does it work? Well, it works via framing, which is ascertaining the starts and endpoints of a bit sequence. So we've got a whole stream of zeros and ones. Obviously, we can see, what it does is it tries to find out how we can divide this into sort of packets, how we can divide, how we can divide it into, into nice packets of containing lots and lots of bits. Okay, it also uses error detection, which is evaluation of whether the packet is corrupt. So it wants to make sure that we're not having corrupt packets, because then that will not work. And it also deals with the MAC addressing on the LAN, which is more than 2 machines. So obviously, if you've got more if you've got too many computers, if you've got a lot of computers on the same LAN, you're going to need MAC addressing to denote which is which. Okay, so the interface to the layer above, which is we receive or deliver a block of bytes if sending on a LAN also needs a MAC address. And we'll recall here the layer above is the network layer. Okay, and the layer below is the physical medium. So maybe I should have put that in. But so where are we? Okay, so we receive or deliver a block of bytes if sending a LAN also needs a MAC address. Yep. And obviously from the hardware must encode and transmit or receive the bits. Okay, that's fairly common sense. Then we go up a layer, and we go on to network layer. And this is going to transfer packets of bytes to any other machines on the internetwork. Now you may think, well, why are you writing internet? Well, why not just write internet? But the World Wide Web is really only one kind of internet. It just happens to be a very famous internet. It's probably not going to be the first. It's not the first one. It's not going to be the last. There's going to be many more types of internet, and it will come with different standards, come with different protocols. But at the moment, that's what we need to know about the network layer. I mean, one of the good things, this model, by the way, is called the OSI model. Another important piece of information. It solely deals with IP. It's IP version 4. There is an IP version 6 because IP. I'll tell you about the differences between those two in just a second. So it works via a global unique address for every machine. So for example, if you've got the IP address 147.127.200.2, it's kind of, we can sort of split it down the middle. So the first 2 digits, 147.127, that's the network part, and 200.2 is the host part. Okay, now what I was going to say about IPv, because of this number range, I mean, it's only like goes up to, it's only like sort of 8-bit numbers we're dealing with. So it's only going to go up to 256. So obviously with IP, so we can't actually go that far with the number system. I mean, there are extra ways of splitting up later, but we'll have to talk about that then. Now, every machine has a forwarding table indicating which data link to use. That's the layer below, to get to every possible network on the internet. So routers have millions of entries, and the machines normally have 2. Obviously, the routers need more forwarding tables because routers are the ones that are going out and getting to all the different nodes on the internet. Okay, so every incoming packet's destination IP address is looked up and either delivered to the transport layer or forwarded. Okay, so it's either going to go forward to another machine or it's going to go up to the transport layer. So interface layer above is a sequence of bytes and an IP address. So it's kind of like, you can imagine that we're adding some more stuff now. As we go up, we're adding more. It's like it's a bit like doing a garden or something. Putting some flowers in, we're putting a pot, a little hanging basket maybe. So we like to, and this is quite a good way to look at it. We just add extra things into it, and and then before we get the finished product that we show to our friends. Okay, now the service expected from the layer below is delivery to any directly connected machine. So we kind of expect this. We kind of expect that the delivery, by the time we get here, we expect that any directly connected machine can be delivered to. Okay, so transport layer. This is to transfer network data between running programs. So we've got TCP, UDP, and some others. And now this is obviously going higher up. Now, also I'd like to mention is that there is actually an interrelationship between these different layers on different machines, which goes, between, in like a horizontal. I mean, in a way, I'm talking in this sort of vertical way, aren't I? But there is also a horizontal connection between these different layers. So transport layer on machine A, transport layer on machine B. There is also this connection as well. Okay. So TCP and UDP give program-to-program transfers, Additionally, TCP provides a reliable data stream. So many people prefer to use TCP because you've got a reliable data stream. Data can go in and out more easily. It uses a port number as the location of the program. So each program that accepts data binds itself to a different port and waits. So yeah, so the computer can have as many ports as you want. A port is it's sort of, it's like a plug socket, like a virtual plug socket. Maybe is a good way to look at it. Each program is you can't plug two plugs into the same socket. So each one is going to want its kind of own thing to do. Okay. Connecting program uses the port number and TCP or UDP added to the packet when sent. Okay, so more stuff is going into that packet. Another hanging basket is put up. Just to note that the web, that's the HTTP is on port 80. So the interface layer above is a socket used to read or write a stream of data created with a port and IP address. And from the layer below, just expects as good as it gets packet delivery to any machine. That's kind of my term. I think it was a film, Jack Nicholson maybe. Okay, so application layer. Now, to provide any network service that can be devised using the transport layer. So we've got HTTP and DNS. There are a vast range that use transport service to communicate. So this is really, getting very near to the actual user now. This is where almost anything goes. So there's all different systems, all different programs, all different languages are going to use different things to communicate, and then that's probably beyond the scope of this actual lecture. And the layer above is a human, and from below, program to program data transfer when given a port number and IP address. So by then it really does expect everything to be done already. So yeah, that was really all I wanted to say about endianness and computer networking. And one of the interesting things is what I'd like to do actually, as I've gone through these lessons. I know I haven't done too many so far, but 1 to 3 they were sort of like some sort of building blocks of binary numbers. Then we had Java in 4, and we had some intro to Mathematica in 5. And then obviously we had an interesting one last time where it was sort of like the introduction to BlueJ, wasn't it? And I did but what I'd like to do is, now we're in lesson 7. What I'd like to do is to use this number 7 to kind of formulate and structure my content. And I would like to have, like, every lesson I have a number 7 in it. I'd just like to have something more kind of, I don't know, more fun. I want to have like a lot more detail in the lessons which have number 7 in it. So if you're looking through this, just try lesson 17 or lesson 27, because they're the ones that I'm really going to try and put a lot more detail. And I hope you've appreciated the kind of extra detail that I've included in this particular lesson, as opposed to some of the generic stuff. I did promise that I was going to start doing Java, but I'm not going to do this lesson, and I'm not really going to do it next lesson either, because what I'd like to do next lesson is I'd like to start to look at software engineering. I'd like to think of all the different models that we've got. We're going to start off with the waterfall model. We're going to look at all the different ways that you can project manage IT projects. Thanks for watching. Goodbye. Actually, there's one little bonus bit I just want to show you. And this graph, it was actually supposed to be part of the main lesson, but I'm just going to leave it to the end here because I forgot to put it in. But it's actually a very important graph, because what we've got here is, on the x-axis we've got time, right? And then on the y-axis, the time is increasing. So if you imagine that sort of bottom left corner of the graph to be like 1949, and then you can imagine the very right of the graph to be sort of 2012. And then if we look on the y-axis, we've got not much, slow, big, and then as we go up, it gets lots, fast, small. Okay, so now you understand the axis. I want to tell you what the actual lines mean on the, this bottom line here, which is running nearest to the x-axis. That's like architecture and operations. So that's all the kind of mathematical foundations of computers and networking. Then once we go up, that's applications. Okay, so the bottom one is operators and just mathematical foundations. The one above is applications. And that can be seen as, so it's maybe there's 3D software coming through now, or something, maybe stuff with Connect or something like that. As you can see, the applications, it increases faster than the mathematical architecture and the operators increase, but not much faster. But if we look at the top graph, I'm going all the way to the sky. That's to do with speed and capacity. And as you can see, that has grown massively more than anything else, okay? Absolutely, it's gone much faster than anything else. And it's to do with Moore's law, and it's to do with, you know, the fact that nano manufacturing is really improved. And I think we're down to about 20 nanometer level. Obviously, we're reaching that threshold. But even so, but yeah, just as a review of the last kind of 60 years, I suppose, we can see that the mathematical sort of underpinnings, and this is something which is very important to know about networking, the mathematical underpinnings have not really changed that much. You know, it's still kind of to do with, you know, very kind of like very, you know, there's certain things that really you know, we really have to understand, because like yeah, I mean, what was I looking at? Binding hardware. I shouldn't really be doing this in the middle of the lesson, actually. But there are, I mean, if you're ever interested, actually, and if you've got this far, you probably are interested, aren't you? So there's a few things I wanted to plug my internet in. There's a few things that I wanted to show you, actually. Let's have a look. Oh, this is fucking absurd, man. Yeah. This guy is a very important mathematician. He wrote a book about set theory. There's very few that I've seen that can sort of oh, he's still going. Yeah. He's a very good mathematician. He's probably my favourite mathematician. Yeah. Sorry, no, I shouldn't. But anyway, he's a very good book about set theory. If you want to learn about set theory, then you've also got this guy. I'm trying to remember what his name is there. This is what the book's called: Elementary Mathematics from an Advanced Standpoint, Geometry. And another one. So there's this one. This is the second one, and the third one is lambda calculus. I haven't actually found a particularly good book about that yet, because what I was planning later on, actually, and this is not something I'll be doing anytime soon, but I really want to look at geometry in much kind of more serious detail. You know, invariance, affine metric geometry. Yeah. Because obviously, you know, it's kind of historical to have an interest in kind of, you know, the parallel postulate. That's the fifth of Euclid's. Well, I won't go into that now. But this stuff, this really provided some very deep sort of foundations of computer science. So if you're really interested in this topic, you know, this is what you need to read. But yeah, I mean, to be honest, not many of you are going to have got this far. So not many of you will see all this good shit at the end, and for that, you know, you can just be happy that you've one-upped your peers, because, you know, you have. All right, this really is the end now. So goodbye.